Alright, so today we're going to talk about C programming and just give you a basic introduction. But before we go there, I'd like to show you, a map of, all kinds of different languages that have been created over the last number of decades and how they link together. And it turns out that actually Fortran was a very important language, and after that, through this actually languages like C got developed and so forth, but C has become a very important central point in this connection graph. This is, by the way, in Dutch. I'm from the Netherlands and I still receive the Dutch newspaper, so I saw this picture and I thought it's so cool to show you this, and we're going to focus on C in this lecture. You have set up Eclipse, with which it's kind of an editor, right? And you can compile C, we will talk about it in a moment, what that means, into an executable that can run and then execute what you had in mind when you coded things up. Now, later in the future blocks, we're going to work with Atmel Studio, which is specifically for your microcontroller. So again, it's an editor, you plug in your C program, and now it compiles to an executable that can then be uploaded on your MCU processor so that it can execute over there. So, so the C programming language was originally designed by Dennis Ritchie at Bell Laboratories. I think he got, together with Ken Thompson, he got a Turing Award, if I'm not mistaken, for their contributions. C is the mother language of many languages used in systems programming, and is procedure oriented. So you will notice that you will be coding up procedures or functions, and you may have already done so when you started working on some of these assignments. So how does it all work? Well, first of all, what is compilation? The point here is that you start off with source code. It's written in C, which is what you learn. But then what does the compiler do? The compiler is actually taking the source code and starts to pre-process this. First it removes comments. I like you guys to put in comments in your code because you want to be able to understand your own code later on yourself. We'd like to be able to explain it when the moment comes to colleagues, to us, to anyone, to anyone. And besides that, later on, comments will really help you to collaborate in proper ways in the future when you set up projects. But the preprocessor is removing any comments because, they do not contain any instructions or declarations. But there are also other kinds of symbols like this one, and you include like an stdio.h, which simply means that's the header file of a source code that's called stio.c, and the source code has all kinds of functions defined, and the functions that are defined are listed in this header file. So that header file is going to be so these commands are being removed as well, but the preprocessor definitely remembers that you are interested in those functions, and later on it is figured out which functions you actually used in STIO in order to get your program going forward. So the C compiler is now going to change this into assembly code. Now assembly code is specific to your processor itself. So each processor, anyone that you buy in the market, has its own instruction set architecture. And so the C code, which is a global language, can be used for all of these processors, but the compiler needs to know how the processor is dealing with it and translates your C code into what is called assembly code. And later in the course we actually have a look at some of this assembly code just for you to have a look at what it looks like. Now, the assembler now takes this and adds those functions, the libraries that you have been interested in, creates an object code that is called, and then a link editor is going to link in those library functions that are referenced in your source code, like a printf statement or things like that. And all of that is now being put together and then translated into an executable file, which is simply a binary, meaning a bit string, effectively, that is being put, that you actually put in your memory, and then you can start running that, and your processor will interpret those bit strings per memory location in what should be done. For example, a jump instruction, or whatever you have, like registers that you want to add together. Now, we will not go that low level, obviously, but it's good for you to at least have a look at or see what is involved in getting finally, at the end, this executable code in your MCU later on. Now, in Atma Studio, we will be interested in yet other libraries that are specific to the MCU processor itself. And we'll come to that when the time is there. So for now, what is a C program? So, first of all, you have some include files like stdioh, stdlib.h, things like that, some libraries that you're interested in. The actual code, once it is compiled, right, and it's loaded up in your MCU, or now in your laptop, it starts executing right over here. It starts executing this main function. It's a function, and for that reason it uses the syntax of functions. That means you have to indicate what kind of output you're generating. So it happens to be int. It doesn't really matter here. Anything could have been decided upon when the C language was developed. There's no arguments because you're just starting it. If you want to get information from the user, you will ask the user, right? Can you give me, can you type something in on the console, and then I can interpret it as the main program, and I can do some, computation with that. So I could do that. But in this simple program, you have an hello world, and a function always ends with a return statement. In this case, for good syntax, right, we just return 0, which is an integer, and that's it. So the include statement here, the preprocessor that you just talked about, is going to load the contents of the header file, which in this case allows standard input-output operations. The main over here is the driver function of a C program. This is where execution starts, and int means it returns an integer value. The bodies always start with, this curly brace, this one, and it ends with the compatible curly brace. Let's have a look at stdi.h. What does it look like? It's simply a list. Again, you have a bunch of definitions and so forth, but anyway, some other header files over here, like other libraries that you would like to have. If you want to use, use the function specified in here, and you simply have a list of functions. So there's a printf functionality, there's a scanf functionality, and more. Okay. So, as an example, you could define your own macros by using this define statement. So if you do this, for example, in this particular case, I define begin to be equal as this bracelet, as this curly brace. As a matter of fact, the preprocessor, wherever it sees begin, it will simply replace it by the curly brackets, and then after that interprets it as a C program. So I could create a macro over here that says while something, curly bracket open, close, do something in the middle, and wherever I see then this particular string in the rest of the program, the preprocessor will replace that word by what I had put over here. And after that, it's interpreted as a program. So in this particular case, begin and end words are quite nice for the eye. You may want to use that, for example, maybe not. I like it. And the body of main here is now enclosed in the begin and end statement, because it will be replaced, as I said, by the preprocessor by these curly braces. You can have other things. Here we have a max array size that we define to be 100. Actually, that's something that we'll do a lot. There's a question.
So if you define begin as curly brace, would you not be able to use a variable name that has the word begin in it? Like, would the preprocessor just say I have like a, I don't know, begin computation as like a variable, would I not be able to use that? Would it interpret it as curly brace computation?
It depends a little bit on whether there's a space in between or something like that, but it will parse your whole C code, and yes, wherever you had another meaning intended to begin, say a variable called begin, no, that will be parsed and would be replaced, and that would actually make a problem out of your C code. But these kinds of defined statements are very illustrated. It's a great illustration of its usage. For example, we will be, if you use this, in your program, you never use 100, but you always use max array size. Now, why would you do that? Because if you then read your program, you can interpret your own program by seeing, oh, here is where I meant to have some statement that's compare something with respect to the max array size. If I would have put 100 in the program, how do I know what it means? In other words, I can create meaning, semantic meaning, to creating sort of phrases that are actually constants that I define a priori in my program. Now, why would I do that? For example, I create a LED that is going to blink, right, at a certain frequency. I'm not asking the user to type in the frequency, but I could up front, for example, says LED frequency and some number. And next time when I want to test my code for another frequency, I only have to change that number. I do not have to go throughout the whole program and make all those changes happen. So this is a good programming style. It helps you understanding what you have been doing. So there's all kinds of keywords, all kinds of phrases, letters, and so forth in C. So what do you use? There are keywords. These are reserved words. For example, int stands for integer, and you can declare a variable of the type integer. Or float, you can declare a variable of the type float, which is just using floating arithmetic. There are instruction keywords like if, else, for, while. Identifiers are a different class. This is a sequence of letters and digits, nothing else. Must start with a letter. And these are used for name variables and functions. So you design your own program, you create a function. You probably would like to create a function name that illustrates what the function is actually going to do. So you create your own name. Identifiers are case sensitive. Valid ones are, for example, root. Get character, there's this underscore here is also allowed, and so forth. Not valid is if you start with a number, you need to start with a letter. Not allowed is if you use one of those reserved words. You cannot do that. If you use this symbol, well, you're not allowed to do that because you want to use characters and so on. A space is not allowed. Constants, as opposed to variables or function names, right, that you create yourself and declare of a certain type, you may also have constants like 13 or the character a or something like that, which is 1.3 times 10 to the power minus 5. So those are constants that you will use in your program as well. String literals, a sequence of characters in close and double quotes, is called a string. How is that coded up, by the way? It's actually coded up and stored in your memory as a series of characters, and then the string ends with the so-called null character, which is added to this whole thing. We will come to that later when next block we will talk about the LCD screen, and you will see that is actually important. Now 13 over here is a string because it's enclosed, but it does not represent the number 13, right? It represents a string. There's no semantic interpretation, nothing. Clearly, A and A with double quotes are different. This is just one character, while this is interpreted as a string, as an array of characters. Happens to be a very short array, but that's the difference. Operators, you can do arithmetic, like plus, minus. Logical operators, you can do and, or operations and so forth. We will get to that in a moment. You will use a lot of white spaces, obviously. New lines, tabs, comments, and so forth. Comments are enclosed in these types of symbols, in green here, the slash with the star and so forth. And these are used, spaces in general are used to separate identifiers. That's very important. That's how the compiler is parsing through your code. Alright, basic data types. There's the character that I just talked about, which is actually stored as 8 bits. You can have an unsigned and a signed form. Let's not get into these details right now. A short integer has 16 bits. An integer can be either a short one or a long one, and a long one is 32 bits, so you reserve simply more. You are able to represent such an integer with many more bits if you expect very large numbers to be dealing with. Again, unsigned or signed interpretation of what those bits mean. Float is an approximate precision of 6 decimal digits, which we call single precision, while double means double precision with 14 decimal digits. So if you want to have more precision, you can use a double. But obviously, it needs more handling in your computer. As a matter of fact, when we're talking about MCU programming, we have a very simple processor, and often we would like to reduce the amount of computation done by the MCU, because it also needs to, for example, deal with very fast, say, pulse width modulation for generating, say, music. Well, if I want to listen to music, then that MCU of mine needs to produce the right changes in the pulse width modulation very, very fast. I do not like to use floating arithmetic because it will take too many cycles and I cannot hear a good music sound. What I want to use is very simple approximations using even simple Boolean operators to make that happen. We will not do that this semester, but it's just for you to know that these kinds of things are important. Numerical constants here are stored as an int type. Numbers with decimal point are stored as a float or a double. Character and string constants, we have special ones, like this we already did. This with single quotes is a character, but you have special ones like this. These are also characters, presenting new line, a tab, and so on. Why would you use those? If you do a printf statement, you may want to skip in your console to the next line, and if you want to do that, you want to print this character, which is interpreted as a new line on your console. A sequence of characters in double quotes is called a string constant or string literal, so you could define constants like that as well. So, variables, very important. We have two kinds really, but before we get there, let's talk about naming a variable. We already talked about it a little bit. It needs to be a valid identifier, not a keyword. Names are case sensitive. Now a variable has a name, also a type, a size and a value. So the type is what we're going to declare. A variable is, for example, of a certain type, and I can declare multiple variables of the same type in one line. I can even combine the initialization or declaring of a variable over here together with an initial value. So I can say the variable should be equal to some kind of expression. For example, here we have one float epsilon equals 1 to the power 10 minus 6. So what does that mean? I declare the variable and at the same time I assign a value to that variable, which is this small value. So here are a couple of other examples. Now there's a difference between global and local variables. Global variables can be used anywhere in your main program, but also all your functions can make use of those. We will be working a lot with global variables in our MCU programming because we would need, for example, a counter that is being updated using one of your hardware timers, and that counter needs to be accessible by a lot of your functions and also in the main program. So we make it a global variable. The local variables are local to, say, the function in which you declare it. So they declared inside some functions. And that means that they cannot be accessed by any other function. So the lifetime of the local variable is this entire execution period of the function. Now, You could potentially also put local variables elsewhere, but let's not do that. So don't do that. And make sure that the local variables are always at the start of your function. Alright, so here's an example. So look at this. We have the includes of the libraries that we're interested in. We create a global variable, declare it here, that we call pi, and we assign it some initial value. Well, we interpret it as pi, so we put this here. Then we have the main program. Look, it's of integer. There's an open bracelet. There's a close bracelet. It ends with return. The first thing that you write down in your program is this line, and that line. And then you start putting in everything else that you want to put in the middle. Now, what do? You may have a local variable. For example, this one, RAD. Because I'm going to print on the console, enter the radius, and then I'm asking the user to give me that particular value for the radius that I want to compute on. This is the syntax. This particular symbol, %f, indicates that the value should be a float. So this means that I expect a float to be put in by the user, and what comes in is a value that has the type of float. That is how it is being interpreted, and will be assigned to RAD. Forget about this particular symbol for now, but you have to write it out like that. A little bit of background though. RAD has is a name, but how do I know where this is stored in memory? It turns out that there's also an associated pointer that points at the memory location. That pointer location I actually retrieve by adding this particular symbol. And then when I read something, then what I read is stored at that memory location. That's all that it means, but you don't really have to remember this, as long as you know that you need to use the symbol in order to get the value that the user gives into the variable called RAD. Alright, so then it's interpreted, and there's some execution going on over here, where some area is computed and being printed, and if the radius was actually a negative number, you may have an error handler which says, wait a minute, that's not what I expected, so that's wrong, user, do something else. You know, good programming often also includes error handlers. We'll not pay any attention to that in this class, but that's something you may want to think about as well. Alright, arithmetic operations. So what do we have? We have this, for example, means A gets the value of B. A plus B adds A and B together, minus, multiplication, division. Alright, and this modulo operation. So let's talk about those two to explain what that really means. Take an integer values 11 and 4. If I divide 11 by 4, it simply means it gets the value 2, because two whole multiples of 4 are included in 11, but the third multiple of 4 does not, because that's equal to 12. It cannot be included in 11. There's a remainder. 2 times 4 is 8, and the remainder is 3, and that remainder is computed over here. So that is what it means to do the modulo arithmetic. Now, it's sometimes helpful to shorten some code, so you may want to know what's going on here. Comparison operators. You can also compare like in an if then else statement and